Good morning, everyone. Thank you for joining the NOAA Central Library and the National Weather Service's Office of Water Prediction for our seminar today. A few logistics to start us off. This seminar is being recorded, so if you place any questions in the chat or any comments, those will be recorded and passed on to the speakers to either answer or get back to you after the seminar is over. And with that, you're muted, so you can't verbally speak, but you can put questions in that question panel, as I mentioned, and we will get to all questions at the end of the seminar. And with that, I'm going to turn it over to Edward Clark, who is going to introduce our speakers today.
All right, good morning, folks. Pleasure to be with you this morning. I'm extremely pleased to introduce two of our speakers this morning. Dr. Trey Flowers is our Analysis and Prediction Division Director here in the Office of Water Prediction. His group maintains, supports, and develops the current and next generation versions of the operational water modeling, freshwater modeling capabilities that NOAA deploys to deliver the mission to protect lives and enhance the nation's economy. Our second speaker will be Dr. Fred Ogden, our senior scientist at an ST position here within the Office of Water Prediction. Fred comes to us from the University of Wyoming, where he was a professor of over 25 years with expertise in model development and hydrology, as well as hydraulics and all things water related. So very pleased to have both speakers this morning. And with that, I will turn it over to Trey. Trey, take it away, please.
Thank you so much, sir. Lauren, if you would advance to the next slide, please. Okay, so the National Water Center, where Director Clark was just speaking to you from, has been a physical facility since its opening in 2015. But we only just received our statutory authorizing language under Public Law 116-271, which was signed into law on New Year's Eve of 2020. So it laid out several expectations and functions for the National Water Center. So it is anticipated to be our research and operational center of excellence for hydrologic analysis for the country. And most importantly here, particularly to this discussion today, is it is intended to be a center through which we can facilitate collaboration across federal, state agencies, academia, the private sector, on all matters related to water resources. Next slide, please. So within that authorizing language, it did lay out several expectations for us. And those were that our goal is to help understand stakeholder needs around water resources and to improve the understanding of our water resources in the country. We are also directed to develop and implement advanced water resources modeling capabilities. We facilitate the transition of research into operations. This is one of the things that I find particularly appealing about our mission, is that we are doing something that benefits the people. We are creating something that does have an operational endpoint. We're not doing science just for the sake of a journal article somewhere. Equally as important is that we're authorized to deliver analyses, forecast, inundation information for all hydrologic events. And this is not just flooding; it is also water resources outlooks, droughts, the dry side as well. And then getting back to our stakeholders, we're also Lauren, would you stay on the slideshow, please? Thank you. So we also provide the decision support services. As we like to say in the Office of Water Prediction, that the inherent value of even a clairvoyant forecast is zero. if people cannot take that information and use that information for to make decisions that are important to protecting their life and their property. So next slide, please. All right, so the vision of the Office of Water Prediction, you know, the Weather Service, we have an overall vision to provide a weather-ready nation. The Office of Water Prediction and the National Water Center, our piece of that is we are pushing towards a water-ready nation. We have extreme challenges in this country related to too much water, too little water, water of insufficient quality for its intended purpose. And our goal is to help the nation as a whole deal with those challenges, creating that true water-ready nation. Our mission, and you know, I'll highlight the first word of this mission is our mission is to collaboratively research, develop, and deliver state-of-the-science analyses, forecast information, and to inform critical decision makers. So, you know, I highlight the word collaborative because even though we are an organization and we are a center, we cannot do this alone. We rely on our partners across the federal government, state governments, emergency management community, the private sector, academia, to do the work that we're doing. We are definitely not on our own island. Next slide, please. And so getting into the work that we're doing to help support this mission, this vision, to fulfill the directive that was in our authorizing legislation, we've been developing the National Water Model. The National Water Model was originally proposed in 2011 by the Consortium of Universities for the Advancement of Hydrologic Sciences Incorporated, affectionately known as COASI. They first proposed this as a community model. There was a great deal of interest in the academic and research communities, but ultimately that effort lacked the agency's support, and it did not advance beyond that original proposal. In 2014, the National Weather Service, NOAA, the Department of Commerce, and legislators on the Hill recognized the potential for predictions outside of our traditional forecast points. I really wanted to push us into a nationally consistent, advanced, state-of-the-science water forecasting capability. And out of that, in 2016, was born the version 1 of the National Water Model, which was our first ever operational water prediction tool running shoulder to shoulder on the Weather and Climate Operational Supercomputing System with all of the weather models that support the mission to protect lives and property of the National Weather Service. We most recently released version 2.1. That was released on April 20th of 2021. And that extended our coverage to Hawaii, Puerto Rico, Virgin Islands, and portions of Alaska. So next slide, please. So what is the National Water Model? If you look at the map here in blue, this is where the National Weather Service across our 13 river forecast centers currently provide an official forecast for water resources. The streams in blue here, they represent about 110,000 river miles of forecast locations. And Lauren, if you would click once for the animation. The red here is the coverage of the National Water Model. It gets a little bit muted in this slide, but in the National Water Model, we're able to provide nationally consistent forecast information at over 3.4 million river miles and growing. So the greatest benefit out of the National Water Model is we're providing information where no information was previously available. Next slide, please. So as I hinted to earlier, we've been aggressively developing the National Water Model. Its first implementation in 2016, operational upgrades in 17, 18, and 19, where we expanded the domain to Hawaii. We introduced ensemble forecasting capabilities in our medium range. We improved the forecast. Version 2.1 was recent in 2021. That was the expansion to Puerto Rico and the Great Lakes, improving forecast downstream of reservoirs. We are currently in the final stages of development of version 3.0, which is our next upgrade due next summer. That will be a very significant feature enhancement for us. That will be, for the first time ever, we will be deploying a continental scale compound flooding total water level forecasting capability. That is the capability for the 120 million people who live in the coastal zones to get a forecast that combines the effect of storm surge, tides, saltwater processes, as well as freshwater processes. We're also expanding the domain into Alaska and making other improvements. And mostly what we're here, after I hand this over to Fred, mostly what we're here to talk about is the version that is beyond the next version. The version that we're planning for 2025, which will be based on the next generation water resources modeling framework that I'll hand it over to Fred now to walk us through the underpinnings of that particular effort. Fred, the floor is yours, sir.
Okay, thanks, Trey, to everyone here.
You're breaking up a little bit, but we can hear you.
Okay, let's go to the next slide, please. So I want to talk a little bit about the current operational National Water Model system and its formulation. And the upper left figure shows that NOAA-NP is applied on a 1 square kilometer grid to do the land surface flux calculations. Runoff that is predicted by NOAA-NP is routed on a 250 meter grid using a quasi 2D steepest descent approach. Similarly, the lateral subsurface flow that is calculated to come out of the NOAA-NP model is routed on a similar 250 meter grid using a Boussinesq approximation. Water that percolates out of the soil is put into a conceptual nonlinear reservoir and sent to streams. The water that goes in the streams is routed using a Muskingum-Kunj hydrologic routing. And as Trey mentioned, we recently added basic reservoir release data where available, and that had a big effect on improving forecasts downstream from reservoirs. Next slide, please. Now, when we look at the performance of the National Water Model, particularly we focused on the version 2.0 retrospective simulation, which extended from 93 to 2018. If we're in the business of predicting inundated area, then peak discharge is a very important variable that we're interested in. And we looked at that entire period of record, comparing it against the instrumental record at stream gauging stations to see how well how well the model performed at predicting peak discharge. And the results are consistent they indicate that the model performance varies regionally. And the variation, you can see that there's a tendency in the Pacific Northwest say cooler, wetter climates, the Northern Rocky, the Pacific Northwest, and parts of, say, Michigan it does better. On this plot, it's a little bit hard to see, but bigger dots are better. They're within plus or minus 25% in the percent error in peak discharge. The smaller dots have greater than plus or 25% on 50% of the events, so that's in the median sense. So the take-home message from this analysis is that, at least for predicting peak stream flows, that the performance of the National Water Model as it's currently formulated varies regionally. And that started us a few years ago, I think in 2018, to think about developing modular formulation, adding those modules so that we could test different approaches in different places, acknowledging that perhaps the current formulation isn't the most appropriate for that scene. I'll just also point, the violin plot shows the distribution of the entire network, and you can see that in the median sense across the entire network, our error in peak discharge is about 45% or so. Next slide, please. So, Office of Water Prediction has a community advisory committee for water prediction. And in 2019, before COVID, that committee met, and the recommendations from the individual members indicated a few things that would be good. One would be articulation of requirements for further development of the National Water Model. Second one would be an emphasis on improvement for observational data and potential sources of data. And we followed through with that, of course, with the addition of the reservoir release data as a good example. Another one would be emphasis on improving data assimilation techniques and processes. And then the fourth one, stand up a community development engagement process, governance and center, and pursue proven mechanisms for community adoption. And we focused a lot of effort recently on that. Next slide, please. As part of the internal assessment of the National Water Model performance, OWP engaged the services in 2019 of the General Services Administration 18F Group, which is named because they're located at the corner of 18th and F Streets in Washington, D.C. They're a group of computer science experts and rotators, and they audited the National Water Model Code. And they came away with 6 recommendations. One is that working code is the best way to determine the path forward. So if we're going to continue development of a more modular model, we'd like to start with a modular model. Second one was to develop a team and leadership structure to support acting on a unified vision and direction. Third, borrow from industry open source development practices. Fourth, treat interfaces as products. So that's a good way to help engage getting people to contribute code to this new model or the new modeling framework. 5, build for sustained development over multiple years and changing team members. And then 6, understand and celebrate the National Water Model community. Next slide. Now I want to talk at some length now about hydrologic predictability. If we think back to that plot that showed the spatial variability of current water model performance, note that formulation seemed to do better in wetter, cooler climates. And if we think about all of the possible storm flow generation processes or mechanisms, you can kind of think of it along this spectrum. Let's go to the next slide. On the left end, we have land surface dominated mechanism, which is common in impervious and disturbed soils, urbanized situations, situations where it's deep, groundwater is far below the land surface, where there's perhaps surface sealing from wind-blown clays, common in arid, semi-arid climates, or frozen soils. And it's very sensitive actually to the storm flow generation is very sensitive to the ratio of the rain rate to the potential infiltration rate, as shown over on the left-hand side. Next slide. On the right-hand side of this diagram, we have a groundwater-dominated system where it occurs primarily in humid climates with coarse soils and shallow bedrock. Both of these end members, you can think of that way, we have pretty decent theory that describes those. The left-hand side is, the good old infiltration excess mechanism. It's highly sensitive to the rain rate, but it generally involves a pretty small number of parameters related to soil infiltration and perhaps surface roughness. On the right-hand side, that's more of a top model type domain where the behavior is pretty well understood. It's very sensitive to the water balance, antecedent moisture, and the time of year as it affects ET. Next slide, please. So on the left-hand side, infiltration excess, a parking lot is a fantastic example of that. And most urban soils have been heavily disturbed, compacted, and altered so that their infiltration capacity is greatly reduced. Next slide. On the saturation excess end member, that photograph shows a slide I took when I was working at the University of Connecticut of a very nice groundwater-dominated catchment. We had monitoring wells in this catchment, and that stream water level is very indicative of the state of the water table in the catchment. You can see the soil there is mostly large material. It's a great example of a saturation excess type runoff catchment. Next slide. Now in the middle, where we have soil-dominated hydrology, we have very low predictability. And this is a major limitation of where we are today in the state of science regarding hydrologic prediction. Lots of things are important in that part of the domain. It's just the complexity is overwhelming. If you try to develop a process or phenomenological model that includes the effect of layering and anthropogenic effects and macropores and transient phenomena related to, say, seasonality and freeze-thaw or shrink-swell cracking, heterogeneities at all a range of scales, and bioturbation, all of those things really make it very low predictability, requires a large parameter space to describe, and it's sensitive. Basins can transition between more of a rain rate sensitivity or a water balance sensitivity depending on the situation. Next slide. And this photograph shows exactly the situation. This is provided by a farmer from Iowa looking down a fence line after an April thunderstorm. So this is before the crops had been planted. But you can see the huge difference in the behavior of those two different fields depending on the agricultural practices. The one on the left is standard tillage practices that involve a lot more driving machinery on the field, and it destroys the preferential flow paths and other things that allow water to get into the soil. On the right-hand side, it's primarily uses a lot more chemicals and kind of a no-till practice. Next slide. So in this soil-dominated hydrology region, we lack a comprehensive theory of storm flow generation. Somebody said once, to understand the subsurface is to destroy the subsurface. We have a very difficult time understanding all of the possible flow paths and how those evolve and change with different land use practices, et cetera. It's a really challenging problem. So at the end members of this figure, we have high predictability, relatively low uncertainty with a smaller number of parameters. But in most of the country, it isn't that simple. So it's lack of a comprehensive theory in storm flow generation is the major problem that the research community, I think, can help us to overcome. Next slide. So this is just a blow up of that picture. I think it's a remarkable example of the same soil, the same slope, the same land use, the same precipitation, but vastly different performance that just illustrates how challenging this predictability problem is. Next slide. A review of the hydrologic modeling literature shows that hydrologic models formulated for specific dominant local processes consistently outperform general models when appropriately applied. And that is the uniqueness of place characteristic of hydrology. Secondly, models with fewer parameters that describe dominant processes outperform general models that emphasize process through parameter values. That's the parsimony argument. If you develop a model with an enormous number of parameters, parameter identifiability becomes a major impediment to improving understanding because parameters interact and offset each other. And then finally, given the lack of comprehensive storm flow generation theory, there is no one model to rule them all. It's likely that there are multiple models that might perform equally well in similar situations. Next slide. In terms of the motivation, the scientific motivation for NOAA's engagement in developing this next generation framework, it's true that federal agencies struggle with model selection, identifiability, and interoperability. Legacy codes and heterogeneous computing environments impede advances because, for instance, almost every model that's been developed comes with its own unique data model, and that makes interoperability very difficult. And then finally, contemporary open source software development encourages collaboration, evidence-based selection, identifiability of appropriate model formulations, and promotes interoperability. Next slide. So the proposed solution that OWP developed, after considering the recommendations from our Community Advisory Committee, from the code audit by the 18F group, and then our own experience with trying to modularize and modernize the current operational national water model, was that we needed to develop a computational framework that allows arbitrary methods or models to calculate fluxes of interest and integrate them over arbitrary timescales and control volumes. We'd like to do this development in an environment that appeals to domain scientists, using contemporary open source software development methods to provide maximum flexibility and ease model interoperability that will allow evidence-based evaluation of different approaches, and that will provide kind of a common framework to take advantage of each agency's considerable experience in their area. Next slide, please. The enabling technologies and standards that the next generation, there you go, thank you, that we will take advantage of come from computer science and engineering with the prominence of Git and open source developments, the basic model interface developed by the Community Surface Dynamics Modeling System, CSDMS, basic model interface standard for model coupling, newly developed geoscience data and standards, WaterML 2.0 has provided a high features data model, which allows a consistent description of the hydrologic landscape. And then the knowledge that we've gained over the last 50 years from hydrologic science and engineering and different model development paradigms. So the intersection of these three things point the way towards this open source community and standards-based development paradigm. Next slide. The next generation water resources modeling framework requirements were identified during a joint NOAA, U.S. Army Corps of Engineers, ERDIC, USGS, and U.S. Bureau of Reclamation workshop in late 2020. We'd like this framework to be model agnostic with maximum flexibility so that as models, data sources, and needs change, the framework can accommodate those. We'd like a common architecture to avoid duplication and promote interoperability. We'd like to do open source development that will promote code reuse and improve development efficiency, provide an authoritative repository for federal water models, and ease and encourage participation by partners and the hydrologic research community. We'd like to apply standards where applicable for coding, coupling, data and metadata, model verification and validation and test data. And above all, we'd like this to be as friendly as possible to domain scientists and engineers. Next slide. The framework objectives that we identified are to engage federal and academic research communities using an open source standards-based development, well documented with examples, model agnostic focus on interoperability, linked with NOAA and other weather and climate models, to ease scientific evaluation of coupled methods and models, running on hardware from laptops to supercomputers, and be domain scientist or engineer friendly in its coupling interface, with a target of 2 weeks for a domain science or engineering graduate student or new employee to add new functionality to the framework. Next slide, please. And here's an example. This is a comparison of a finite difference groundwater model versus top model in a catchment with thin, shallow soils. If we look at this, the hydrograph on the top left shows hydrographs predicted by the two approaches using similar parameters and approaches. And you can see that in this example, the hydrograph is pretty well preserved. If you look at the soil moisture dynamics on the upper right-hand plot, in the finite difference model, the groundwater table, when it's raining, rises uniformly everywhere until it reaches the ground surface. But it doesn't fall uniformly everywhere when it's not raining, and that gives rise to this hysteresis effect. That's pretty interesting, but it doesn't affect the hydrology of the runoff response very much. The point where the water table intersects the land surface doesn't change tremendously with that effect. So the hydrograph performance or comparison indicates that a model like top model in that setting is really good for predicting flow. It saves a lot of CPU cycles, but it doesn't simulate the water table dynamics correctly. And is that important? If it is, then perhaps you might want to reject that model as being appropriate. But if you're primarily interested in runoff or storm flow generation, it seems to be appropriate. This is just one example of many of things where if you could test different approaches in the framework, you could identify approaches that are that meet your requirements. Next slide, please. So allowing diverse model formulations. There's nothing in the specification for the high features data model that requires the use of a model with a particular formulation or that uses any particular discretization. You could take a catchment, you could conceptualize it in any number of ways. And there are settings where each one of these different modeling approaches shown on this slide are perhaps applicable and appropriate, including, the big one that everyone's doing a lot of research on right now, which is, the machine learning type approaches. Next slide. The data model that we have selected, WaterML 2.0 high features data model, delineates catchments, streams, rivers, lakes, reservoirs, and estuaries using a standard terminology. Next slide. So you can take that setting and you can break it up into identified catchments, each with its own model. Catchments contribute flow to a nexus, which is a connector, could be to a stream, which is called a flow path in the data model. And these individual components can be linked together to describe the connectivity of the network And finally, you know, we've got a lake or a reservoir shown there towards the bottom of this set of catchments, and then it could flow into an estuary, which we would treat as another water body. So this kind of abstract data model provides a common standard vernacular for describing the characteristics of the landscape, and we call that hydrologic set of hydrologic features the hydrofabric is what we call it. And it would include all the base data that underlie that, including the high resolution DEM, the high resolution soils, land use, land cover, etc. Next slide. We have adopted, based on input from the other agencies that we've talked with, the basic model interface, BMI standard, with an extension to make it work in a high performance computing environment. And that extension is shown in the red box there that you see. The BMI interface has been around for about 10 or 11 years. It provides published coupling interface for community models. Code compatible with one BMI model can be used with any BMI model without knowing its internals. It supports multiple programming languages. A BMI model realization gives the next generation framework the flexibility to immediately use extended community models as long as they implement the BMI standard. And it provides a mechanism to separate model development from core next-gen development needs. Now, the extension to, I'll just talk briefly, the extension to HPC allows a new set of BMI functions that can tell a running model to stop, save its entire state, which would be all of its internal state variables, all of its internal counters, time steps, everything that's important to restart that model from the same exact state and write that either to memory or to disk. And that will allow an HPC system to perform load balancing by either load balancing or checkpointing, by telling the model to stop, save your state, I'm going to move you to another part of the machine maybe that's not as busy, and restart you. So that's a significant enhancement to the approach for supercomputing. Next slide, please. Now, the other thing is there are very few complete hydrologic models out there that someone might want to test. Often models focus on a particular set of or subset of dominant hydrologic processes. You know, you might have a model that's really great at predicting runoff, but it doesn't have a great snow melt component, or maybe you want to test it with a different snow melt modeling component. So the next generation framework envisions coupling and a BMI coupling with models and modules for different processes. And that opens up a question of meta modeling. How do you construct a model from components in a way that's consistent? If you have more of a conceptual model, such as the one on the left here, it's pretty straightforward. If you have a very detailed, discretized, process-based model, like the one shown on the right, now that becomes a different issue, and it's an outstanding problem. For that reason, we're focusing early in the development of the Nextgen framework on models that are more like the model on the left than on the right. Next slide, please. Now, this is an example, the conceptual functional equivalent to the National Water Model as it is formulated at present. The little lightning bolt symbols are things that are identical to the current National Water Model. The sunshine symbol is a new conceptual replacement function. What this conceptual functional equivalent model does is it eliminates the 250-meter routing grid, replacing it with a GIUH conceptualization for overland flow routing or surface flow routing, and then the lateral subsurface flow, instead of being routed on that 250-meter grid, is being routed using the conceptual Nash cascade. but in general, the rainfall partitioning function is identical. The percolation function is identical. The trigger for lateral subsurface flow is identical. It's just the replacement of those routing functions. And we've developed a modular version of NOAA-NP to calculate snowmelt and ET fluxes as well that we couple this to. Next slide. Now, one of the real strengths of the next generation framework is that we can add and test complexity in an incremental fashion by facilitating the coupling of process modules. We could think about an incremental approach to adding complexity. We don't have to make an a priori assumption about what an appropriate discretization is, what an appropriate formulation is. So in the middle row, that yellow colored arrow, complexity goes from simple to more complex. You could start with a lumped model. You could make it a tiled model where you model percentages of the catchment with different either parameters or approaches, but don't interact. You could then add in a little bit of information about, say, dominant soil and land use complexes, which would give you a semi-distributed approach. And then you could bring in distributed forcing. And each time you increase the amount of spatial information that's brought in, it makes the model more complex. But in the context of NOAA's operational needs, there are many places where there are limitations on the forcing data, their accuracy, and expected errors. And the other thing that we've done is developed a set of tools which we call high refactor in cooperation with a group at the USGS that has allowed us to recast the NHD Plus network into a more uniform and consistent computational hydrofabric. We found that 540,000 of the 2.7 million NHD Plus catchments are less than 1 square kilometer. And by refactoring that, we've been able to eliminate a large number of those small catchments by joining them to their larger neighbors. Next slide, please. In terms of community engagement, we're doing our work in a transparent open source environment. The unification of data models by using BMI, the high features data model, promotes code interoperability so we can stop inventing new data models. That's a major impediment to model interoperability, is differences in data models. We can prevent bug reinvention by sharing code. If everyone's using the same code, and I don't mean everyone has to use it, but the people that are using it, they can fix bugs, they can submit their revisions to the code and fixes and solve a lot of problems, I think. We can support a diverse computational environment, both in terms of hardware and programming languages. Present, the next generation framework supports. The framework itself is written in C++, and it is object-oriented, but it also supports programs written in Fortran, C, and Python. There may be unconstrained use cases for the framework outside of hydrology. Any model that supports the BMI standard should theoretically work with the framework. And then the federal water prediction community can elevate models to a common setting to support scientific evaluation and advance demonstrably superior approaches. And I think that is extremely valuable. There was a paper published a few years ago that showed that hydrologic models are used because mostly what the author of the paper is familiar with, or which academic group they produced their pedigree, rather than which model was appropriate. And in a framework such as this, it takes away the advantage or the need to be a specialist in a particular model. If your model is compatible with the framework and you understand the framework, then any model that's in the framework should be equally easy to use. Next slide, please. So in terms of enabling the collaboration, this stage is set. We've got a transparent open source development paradigm standard geospatial data model and library. We're using the CSDMS basic model interface extended to work in the high performance computing realm. And we're meeting a multi-agency need to promote science and interoperability. And the partners that we've been working with so far, we've got this stock car with all the stickers on the side of it here. We're always welcoming more engagement from different folks. And with the new Cooperative Institute for Research and Operational Hydrology, we look forward to increased engagement with the academic community as well to help make this framework not only, it is real, it exists, but make it live up to its potential. Next slide, please. And this is where you find our code on GitHub. We are looking to, we're doing some testing and calibration of 3 different modeling approaches at present. We're testing that conceptual functional equivalent to the national water model and comparing it against top model and a machine learning approach. And we're working on a publication to describe those early results of the framework in the near future. And I think that's the last slide. So there's our contact information for Trey and myself. Be happy to answer any questions. Thank you.
Great. Thank you so much, Fred and Trey. This was awesome. If anyone in the audience has a question, please place that in the question panel. I'm not seeing any questions yet, but I will let everyone know if you chimed in late. We did record this session, so if you have you had to step away, or if you missed a section of the presentation, it will be up on the library's YouTube channel shortly. And I'm just going to give everyone another minute or so to see if they have any questions. If there are no questions, I'm going to ask Fred or Trey, is there anything extra you would like to add?
This is Fred. Not for me. I think I look forward to working with the community on this project. It's fantastic. Thanks.
Thank you, Fred. And I'll pick up on that as well. You know, as I said in the opening remarks, we're very much open for business in terms of collaboration. We're creating a tool here, as Fred described, that is flexible, that is very much intended to facilitate collaboration. And you know, we're not able to do everything by ourselves, and you know, we have it in our mandate to collaborate. So anybody who's interested in coming and participating and joining in on the fun, you are most welcome to do so.
Thank you. And you guys saved everyone just enough time that they could get their questions in. So we have a few questions that I'm going to ask as many as I can before our time runs out. So the first question is, what role do you see the SAC SMA model, which is a conceptual model, play in this new formulation?
I'll take a stab at that one and give Fred the opportunity to join in later. The framework is model agnostic, so we very much are building this so that we can use the right tool, in the right location for the right reason. And we are not going into the construction of the water model using this Nextgen framework with any a priori assumptions about which is the most appropriate model to use where. We're going to let the evidence drive our decision making here. So any model approach that is viable, as Fred covered very well, there's a time and a place for each model, and where models are most appropriate, that'll be the model that gets integrated into the Nextgen, the national water model using the Nextgen framework. So certainly models like the one mentioned here will have a place where it performs best. Fred, anything you'd like to add?
I think, yeah, that's right. I mean, when I was in academia, I had a lot of engagement with agencies, and one agency in particular liked the model that I developed, but that's as far as it went. With this framework, if you submit a model that you can demonstrate performs well in a particular setting, it's in the framework, anyone can use it, and it's because it's been incorporated into the framework, it's available for others to test. So if someone somewhere, anywhere on the planet sees your paper and sees that your model works well in a particular setting, it's in the framework, they can use it. For our needs, if it does something that no other model can do in terms of meeting our requirements, we will use it. But the beauty is, as Trey said, we are model agnostic. The performance of the model will determine what makes it into the operational national water model.
Great, thank you. Our next question is, what percentage of land is groundwater dominated and soil dominated?
Well, that's a great question. Actually, I would say those end members are actually very rare in my experience. Most of the country is soil dominated hydrology. But that's an outstanding research question, and I think that would be something fantastic for the academic community to answer.
Great, thank you. Our next question, how much does the inconsistency in the NAVD 88 elevations that stream gauge data is referenced to across the country affect your modeling outputs?
I think it has a bigger effect on our flood inundation mapping efforts, if I understand the question right. Trey, you agree with that?
Yeah, I would agree. Our model efforts are mostly to generate the hydrologic volume and to route that around. We use stream flow gauging information at the last step for data assimilation, a process that we know we need to improve upon. But it's certainly a concern for us as we go towards a completely unified model from the freshwater into the saltwater domain. We want to be consistent with our datum. So it is a concern for us, but right now it's not that big of an impact on our model performance.
Great, thank you. So the next question will be, how do you see this new direction interacting with the Summer Institute focus in coming years? Are there specific areas that you plan to address in that forum over the next few years?
So starting from this summer, the Summer Institute is focused on the Nextgen framework and developing, testing BMI approaches for all of water prediction. The particular themes that we'll have in the future will change as we identify new areas where focus is required. But from this summer, starting from this summer forward, the Nextgen framework will be the kind of the organizing principle of the SI.
Great, thank you. Next question. Is calibration of the model done on multiple points in one run, or is it done for individual locations separately?
That's a really good question. We have some staff that are really adept at calibrating models, and they're trying it both ways. Because of the permutations of different formulations, the framework gives us the ability to create an enormous calibration problem to our detriment. So coming up with a smart way to do that is another kind of really nice, interesting research question. If you have a modeling framework that allows you to apply a multitude of different models across the landscape, what is the optimal way to calibrate that system? That's an open research question.
Great. Our next question, is there an expectation that this new framework will be used to determine regulatory requirements?
Fred, maybe I'll take this one. So the National Weather Service's mission is not a regulatory mission. We are developing this framework for, in collaboration with our academic partners or our academic and federal partners, to support a multitude of different outcomes. So we are not designing this specifically with a regulatory outcome in mind, though we hope to create a framework that is flexible, that people can use it to their own ends, using their own individual, uniquely tailored models for that. So it's not our expectation that the framework will be used for any particular purpose, other than, we do have our particular purpose that we are going to use it for, which is developing forecasts in support of the Weather Service's life and property mission.
Great, thank you. I'm going to kind of parse this next question. Could you speak a little more to the ways that NOAA and the Office of Water Protection is collaborating with other agencies, USGS, et cetera, particularly in terms of how the different agencies' hydrological models and modeling will be integrated or not? Will agencies continue to run their own models while they also submit it to the framework?
I'll take a stab at that one. So, yes, both of those are entirely likely and possible. What the framework allows is, by using the standard for model coupling and for the data model for the land surface characteristics, would allow rapid deployment or testing of new models. It could be that after a model is evaluated, compared in the framework, it could run standalone. In fact, one of our requirements is that you don't have to rewrite domain science code. You have to add the BMI functionality, but the model should still be able to run in a standalone mode. And that's really important for unit testing, to make sure that the code is still performing as it should. So with that requirement, it's entirely possible that a model could be used in the framework and as a standalone model as well.
Thanks, Fred. I'm going to grab one or maybe two more questions before we have to wrap up. Is there any specific plan for urban areas and urban hydrology in NewGen?
Sure, we envision hyperresolution modeling capability, where you might apply a fully distributed hyperresolution. By hyperresolution, meaning discretization smaller than say 100 meters or so. But that's still, because we're model agnostic, we don't presuppose what that model is going to look like, what its form will be. It might be somebody comes up with a really elegant model that doesn't require a super detailed, maybe it's a distribution-based model that doesn't require a super high resolution discretization to give you a good result. That's one of the beauties of the Nextgen framework being model agnostic. Develop something, test it. If it works well, it might be used in the operational model.
Great, thank you. And one last question. Will you have a plan to extend the national water model to cover the Canadian territories in the Northeast region? The ocean model in the Gulf of Maine requires the freshwater input from the Canadian rivers.
Trey, you want to take a stab at that one?
Yeah, so in the Northeast region, so I'll take this from so we do not provide forecasts north of the border, because that is our, it's not our domain. We do include portions of Canada in our calculations, particularly in the Columbia River Basin and also in the Great Lakes and Laurentian domain. We do have that in our models, but we're not a substitute for the Canadian provincial governments to, we're not trying to usurp their ability to provide forecasts for the people that they serve. So although that is integrated into the water model, and we will continue to refine that in terms of improving our forecast performance for our stakeholders. We have no specific plans for anything providing that information north of the border.
Thanks, Trey. And we are out of time, but I did find this last question to be very pertinent. So we're going to wrap up with this. How could the interested people in the academic community get involved today?
I would say look at the GitHub site, see what we've done, download the code, compile it. We have some examples there and documentation, and then reach out to us, the team. GitHub provides collaborative environment for people to ask questions and start a dialogue. And it's the way things are being done now in the software world. So your students know how to do it if you don't know how to do it.
And to add to that, Fred, we will have a lot of this work being presented at the AGU Frontiers in Hydrology meeting coming up in Puerto Rico in June. We have 7 sessions there. Our academic partners, we welcome them to come listen to what we're doing and engage with us. We're also planning on submitting a session for the AGU fall meeting coming up in Chicago in December. So folks are more than welcome to come participate in those sessions and hear about what we're doing and learn about the questions that are vexing us and the opportunities for supporting that research.
Thank you so much, Dr. Trey Flowers and Dr. Fred Ogden. This has been a wonderful session. We did run a little bit over, but I want to thank everyone for coming today and sticking with us. We did record this. This will be up on the YouTube channel. Please reach out to Trey or Fred if you have further questions, and I will take the questions we didn't answer and pass them along so they can be answered offline. Thank you all, and I hope you have a wonderful, safe rest of your Thursday. Take care.